Welcome back to ECE 320A. Homework number 2 is piling up in front. I just have to remember to take that with me when I leave the classroom. Reminder to self. There is a review session tonight in the ECE building in the basement, and I believe you'll be able to get there. If not, pound loudly and we'll open up a door. Exam number 1 is the next time you attend this class. It will be Thursday of this week. I hope that doesn't surprise too many of you. I hope you realize that that exam is occurring. And because of that, I will review very quickly the process that I'm allowing for exam number 1. I'll want you to be spread out, maybe a little bit more than what you are now in the classroom so that you have plenty of elbow room. Today what I want to do is actually move into Chapter 12 material. We will have a review session tonight and we'll talk more about all of these phasors and phase voltages and line voltages in that. But today, to get you moving forward through the semester for your next homework assignment, we're going to talk about Chapter 12, which is Laplace transforms. And show of hands, have you all seen this? Laplace transforms? No? Some of it. Well, we're going to try to quickly go through some of the definitions, some examples. This is really a way to go play in a different domain. Instead of always having to play in the time domain, you've already been playing with phasors. That's a frequency domain. Now we're going to generalize that concept in the Laplace setting. Now it will be even more general than just phasors. We will have this complex frequency variable, little s, and I'll probably write that as a script s so that you don't think it's a 5 all the time. We'll go through some basic properties, some operations, and we'll show how you can solve a differential equation with Laplace transform techniques. And then we'll say, well, where did this differential equation come from? It could come from a circuit, and we'll derive the differential equations, coupled differential equations associated with an electric circuit. One of the things you need to learn from this class. Quickly on the exam number 1 process, I believe this has been posted on the D2L website for quite a while. You need to furnish your own one sheet. I'm not supplying that to you. So make sure you create your own sheet. You can write on the front and the back, but make sure it's this standard 8.5 inches by 11 inches page that you're using. I'm going to allow you to use any calculator essentially that you want, which is basically a computer, but we're not going to allow anything beyond graphing calculators. So no computers. Don't bring your laptop in and expect to communicate with your buddy next door. What'd you get for problem 2? Yes? Do the notes have to be handwritten? You can type those up. You can LaTeX those. You can put them in Word. They can be whatever you want. And at some point, when we start doing Laplace transforms, you may be cutting and pasting even some of these tables so you don't have to rewrite those, although sometimes it's helpful to actually rewrite those or copy those down. But you can have your own, and I've seen students, I guess I should probably say no magnifying glasses, that hopefully you don't try to cram that much onto your one sheet of notes. I don't think it's necessary. And I have seen pretty fine writing, which now I won't be able to see, but you can get as small as you want. And bring something to write with. Questions on exam number 1? Yes? It'll be in this room, the exam, but the review session is tonight. It's in ECE 107. It's in the basement of the ECE building. But your exam will be in this room, so don't let that confuse you. Your exam will be in this room. So show up like you normally do for class, but be prepared to fill out an exam. Other questions? And there are practice exams on the website on D2L. You can work those and hopefully get prepared and see the structure, the types of questions that are asked. Let's now talk about Chapter 12. Laplace transforms, and Laplace transforms are your friend. Don't think otherwise. You want to be liking these concepts. One of the reasons you want to like this is because the Laplace transforms are meant to be a simplifying transformation. What that allows us to actually do is move back and forth between the time domain and the frequency domain. And the reason we want to do that is because we can now convert these time domain differential equations into equations involving this complex frequency variable S that will allow us to just use algebra. Complex algebra, but we can use algebra. So we're converting differential equations into algebraic equations. And those are in a different domain. They're now in the frequency domain, and we need to get comfortable moving back and forth between these two domains, the time domain and the frequency domain. Let's now define what we mean by this Laplace transform, or what does it look like. And in this class, we will be working with a single-sided Laplace transform. What that means is our time axis is only involving non-negative values of time, of the real line. Here's our definition for the Laplace transform. We're going to call it now this capital F of S when the time domain waveform is little f of t. And this little f of t will get weighted by a complex exponential, e to the minus st. T is time, typically. S is the complex frequency variable. We integrate with respect to time. Time is going to be eliminated. So we're looking over all of time from time equals 0 minus. We include all of the origin, t equals 0, and we go up to the infinite horizon on time, and we condense all of that down. We absorb all of that information over the time history of this function f of t and cook it down to, or boil it down to, a new representation, capital F of S, which is going to be usually a ratio of polynomials in S. That's what capital F is. The notation that we will use to describe that is we will say capital F of S, instead of always necessarily writing that integral, I might just say that's now the Laplace transform of this time domain waveform, little f of t. Yes, sir. S, as in Sam. Pardon? S is our variable in the frequency domain. S is a complex number. So now when you see S, that can be now this two-dimensional space of real and imaginary values. S can take on any value in the complex S-plane. Keep doing this. The complex S-plane is two-dimensional, has a real axis and an imaginary axis. And S can live anywhere in there. And we will be evaluating things for specific values of S. But that condenses, or that collapses, all of this time domain information into the frequency domain. We have several musicians in here, I believe, based on your passports. But we do all this in our heads all the time. We do Fourier transforms, Fourier series in our head. Our body just naturally does that. We can tell the difference between a clarinet and an oboe, or a trumpet and a trombone. Our ears do that. They're doing this Fourier transform. That's the frequency domain. We're doing the frequency domain processing in our ears. We're now going to do it on paper and pencil by taking this time domain waveform, f of t, and moving it into the frequency domain, capital F of s. Let's see how that works for a specific waveform in the time domain. And one that we use quite a bit is the unit step, which is equal to 1 for non-negative values of time. It's equal to 0 for negative values of time. We know what that looks like then in the time domain. That's pretty easy to think about, the unit step. And a lot of times we will actually use that unit step as a switch. When we're turning something on, we'll say multiply everything by the unit step, and that's like turning everything on. That's what that 0, 1 does, essentially. What does this look like as far as its Laplace transform? We are now really just Laplace transforming a waveform or a signal. You could think about this being in the lab. You might excite your circuit with a step input. You may now put in this step input from your function generator, and you want to see how your circuit responds to that. So we might want to know, well, what does this signal look like by itself in the frequency domain, or what's its Laplace transform? Notationally, we said we would write that then as this Laplace transform of u of t, which we will then call capital U of s, and we want to know what kind of ratio of polynomials does this end up looking like. By definition, this is now this integral from t equals 0 minus to infinity of the function little f of t, which is now u of t, scaled by this complex exponential that has in its exponential part or component frequency and time. So that's dimensionless. You're multiplying these together, s and t. So s is like a frequency term because you want the exponent on that exponential to be dimensionless. And t, you know the units of t, that's seconds. S times t gives you no units, so s must be like hertz or reciprocal of time. Now let's compute this. Over this particular integration interval from 0 minus to infinity, what does the waveform u of t look like as a function of time? It's pretty complicated, isn't it? It doesn't have any time dependence. It's just always 1. And now we keep the integral or integrand there, e to the minus st dt. And I always have faculty members saying, oh, they don't even know how to integrate. Yes, they do. They just pretend they don't know, right? So what's this integral? Don't let me be the faculty member that goes back. Does that look okay? So e to the x, if you needed to integrate e to the x, it would be e to the x. But now x is a little bit more involved. It's now some scalar times t, where t is now our variable of integration. So we have to sort of, if you did it the hard way or the long way, you would say, oh, change the variable to x, and now you kind of have to push that through, and that puts this minus 1 over s out in front of e to the minus st, effectively. Now, let's evaluate these, or this expression, at the two limits. We can now say we have minus 1 over s, e to the minus s infinity, minus e to the minus s times 0 minus. And we won't go into a lot of detail here, but what is e to the minus a large number? That's 0. And e to the 0, there is our Laplace transform of the unit step. That's 1 over s. This is now capital U of s, which is this Laplace transform of u of t. Meaning, if we had these two domains, here's the time domain, and here's the frequency domain. If I'm playing up here, then I'm using 1 over s. If I'm down here in the time domain, I'm using the unit step, 1. Is that clear? And you can analyze this circuit in the time domain, or maybe it's easier to work in the frequency domain. If you have a unit step in the frequency domain, you're going to replace it with 1 over s. What if we delayed that unit step, started our time axis a little later? What will that do to this functional description of the Laplace transform of the unit step? Here's a delayed step. And again, this is a unit. It has an amplitude of 1, is what I'm assuming. What's the picture of this look like? Hopefully you know that it has still a magnitude of 1. Now it's just, where is it 1 and where is it 0? The unit step, the way that I think about it is I go, let me look inside the argument on that unit step. And whenever that argument is non-negative, then that function is going to have a value of 1. I'm now looking at the interval of time, t minus t0, greater than or equal to 0. That's where it's going to be 1. So if I now say t minus t0 greater than or equal to 0, t greater than or equal to t0 is when that's going to be turned on. And I can now go over here, whatever t0 was, maybe that was 4, maybe it was 1.5, it's something, we said it was positive. Now we know what the unit step looks like when it's delayed. A positive amount t sub 0. What does the Laplace transform of that delayed unit step look like? Well, the nice thing is we don't lose everything that we just did. The unit step, without any delays, looked like 1 over s. We're going to still have that 1 over s present in this result, which is a good thing. You should feel good about that, or warm and fuzzy. Now let's see what actually happens with this Laplace transformed delayed unit step. We're now looking at this. Plugging that into our definition, we said, okay, we're integrating from 0 minus to infinity. Our function, that gets scaled or weighted by this complex exponential, e to the minus st dt. But that's why you took the calculus, is so you can play and have fun with this, right? And even when you get older, you can say, you know what? Let me convert this into something that looks like what I just did, right? What did I just do? I integrated u of t. So I want the argument on that u to just be a single variable. I can do that by saying let tau be t minus t0. Let me introduce a change of variable. And then anywhere I see t, I need to rewrite that in terms of tau. And that just means that t in that integral expression, I'm going to just, everywhere I see a t, I'll replace it with tau plus t sub 0. And if I differentiate d tau, t naught was a constant, wasn't it? So this small change in t is the same as a small change in tau. D tau is dt. And our limits on the integral to begin with were 0, or 0 minus and infinity. When t is 0 minus, what's tau? Minus tau naught, isn't it? I just go back to my defining relationship for tau and plug in t equals 0 minus. And then when t is equal to infinity, what's tau? Infinity minus a finite number is still infinite. Those are now my new limits of integration. I now know what I can replace dt with, and I know what I can replace t with anywhere in that integral. So that now this integral, or this Laplace transform of the delayed unit step, is now an integral from tau equal to minus t0 up to tau equal infinity. U of tau, that was the whole point of defining this new variable tau. E to the minus s, that was times t, but t now I rewrite in terms of tau plus t sub 0 d tau. Are we okay so far? And now I can just start manipulating what's going on. That exponential, I can use my understanding of exponentials. I can separate that into two pieces, an e to the minus s tau and an e to the minus s t0. I'm integrating with respect to tau. E to the s t0 is independent of tau. I can pull that out of the entire integral and sort of not have to deal with it. Meaning I'm now rewriting this as e to the minus s tau and e to the minus s t0, and that allows me to factor out that e to the minus s t0 from the integral. And now that should be looking similar to what I had done before, except the lower limit. Darn it. That wasn't minus t0 before, was it? But I won't give up just yet. I have this e to the minus s t0. How about I just write that integral into two integrals? Just split it up. How about if I have an integral from minus t naught to 0, whoops, and wake me up if I fall asleep and write something that's not correct. If I'm on the floor and I'm sleeping, maybe dial 911. Oh, dial, that's the wrong thing to say, isn't it? You're going, what? You've probably never seen a dial, rotary dial phone. So punch in 911. Or if you want to just leave and leave me here until the next hour, I guess that's okay too. Okay. you'll have to live with that. Apparently, I won't be living if you leave me. Where was I? Oh, I was dead on the floor. You ready to go? Then you won't have an exam Thursday. That's pretty good. Now I know what you're going to do. All right, let's keep going here. We have 0 to infinity, u of tau e to the minus s tau d tau. But now we can simplify this a little bit, realizing what the unit step looks like between a negative number and 0. What's the value of u of tau for when tau is negative? That's 0, isn't it? So that first integral is gone, and now I just have to go from tau equals 0 to infinity, u of tau e to the minus s tau d tau, and that we've already integrated in the previous example, right? That's the exact formula that we had before, so I now have e to the minus s t0, and the only thing I have left in this bracket, if you'll believe me, is just 0 plus 1 over s, right? And now this delayed unit step has a Laplace transform of 1 over s scaled by e to the minus s t naught. And t naught was a fixed integer, or not an integer, but a fixed real number, positive, non-negative number. And that's now the Laplace transform of a delayed unit step. We derive that for a specific function, but that's actually a very general result. If you now know the Laplace transform of little f of t, and somebody says, what's the Laplace transform of little f of t minus t naught? Well, now you know that that's e to the minus s t naught times the Laplace transform of little f of t, which is e to the minus s t naught, capital F of s. And if somebody now delays a waveform, you can immediately write down the Laplace transform of that delayed waveform if you know the Laplace transform of the non-delayed waveform. It's just scaled by e to the minus s t naught. And that's a general result. What are some other properties of this Laplace transform? One is something that's called homogeneity. Which is just a fancy way of saying if you scale a waveform, then that's just a scaled, the same amount of scaling on the Laplace transform. The scaling is the same in the time domain and the frequency domain. Meaning if I now have A times f of t, that now produces, that's what this arrow means or implies, A times capital F of s if I wanted to Laplace transform capital A f of t. In this particular example that I'm using, A is a constant, and by that I mean it's not a function of time, t. And it's not a function of f of t either. A is just a number. So homogeneity holds. If you scale something in the time domain, the exact same scaling is going to happen in the frequency domain. That's nice. The other thing that's nice is that we can preserve superposition. Which says that if you had a waveform f1 of t and you knew its Laplace transform, and then you said, oh, I'm sorry, I need to add in another waveform to that. Well, now you just have to know that waveform's Laplace transform, and if you've added two waveforms in the time domain, you can simply add their Laplace transforms in the frequency domain. These two properties are great. You can just feel that, can't you? Well, they allow us now to analyze all sorts of circuits with the Laplace transform. These linearity properties, that's what these are, homogeneity and superposition. These linearity properties allow us then to look at really each of these circuit elements that we'll be playing with separately and then put them all together like we're used to putting them together. Meaning each circuit element or variable can be transformed separately. And that's a big thing. Yes? So I'm not so the question was, are you talking about phasors? Now I'm generalizing this idea or concept of phasor. Now we are going to allow ourselves to work either in the time domain or the frequency domain. And now the frequency domain allows us to deal with systems that are not just sinusoidal steady state. That's the phasor, isn't it? Now, with the S domain, you can enjoy transient response. No more steady state. Or you could have a transient and then you get into a sinusoidal steady state. That's why Bill Nye's on Dancing with the Stars and I'm not, right? You didn't have to laugh. Bill. Sorry, he's not up here. Where were we? Oh, frequency domain. So S is now a generalized version of what you've been playing with this phasor, okay? So now you can do more than just sinusoidal steady state. Now you can do transient analysis with this in the frequency domain, which allows us then to convert these differential equations that maybe you didn't really enjoy quite as much, but really you should have really been keen on those too. But now we can simply go back to our algebraic days and manipulate algebra and solve differential equations by just doing some algebra and knowing how to go back and forth between the frequency domain and the time domain. Now, if that's the case, the first thing that we better learn how to do is, what does a derivative look like in the frequency domain? If you now are saying I can Laplace transform differential equations, you better show me how to Laplace transform a derivative so that I can now, if somebody gives me a bunch of derivatives, I can take those into the frequency domain. That's one of the points. So let's now look at, from the definition, what does the Laplace transform of a derivative look like? notationally, I'm asking what happens if instead of inside the curly brackets, we don't have f of t, but we have its derivative. We're going to show that that is actually this complex frequency variable s times the Laplace transform of f of t minus f of 0 minus. And this is time t equals 0 minus. If that waveform had a non-zero value at time 0 minus, then we have to subtract that off from our f of s expression, or include that as a minus that number. Now, we went from differential equations, which was maybe, what, junior year of high school, down to algebra, which was 4th grade. Now we're going to go down to becoming a 2-year-old. Why? Okay. Why is this true? Why is the Laplace transform of a derivative equal to this expression in the frequency domain? Let's just derive that, since we're into explaining very carefully and thoroughly all of these concepts and ideas to whomever and whoever asks, right? So now we want the Laplace transform of df dt, or the Laplace transform of f prime of t. And you go, shoot, I don't know what he's asking for, but I can write down the definition, which is put the function where it belongs, scale it by e to the minus st, and then integrate over all time from 0 minus to infinity. Now, we have to go back to our sophomore year in high school and remember our calculus. And we go, well, now how do we remove derivatives in the integrand? Integrate by parts. Okay, so now we're integrating by parts. And what we will do is let's define, I'll use variables v and w. Let's let v be e to the minus st. W is what's left over in my integrand when I get rid of the v, and so that's going to be this f prime of t dt. I'm trying to basically get rid of the derivative inside the integrand, and I'll do that with defining dw to be this expression. What's the derivative or the differential of v? Is that okay? So the derivative of e to the x, e to the x. But x is a little bit more involved, and so we have to incorporate that. If dw is f prime dt, what's w? Good, now we've gotten rid of the derivative, because now we can say that the Laplace transform of f prime of t, this is now our integral of v dw. We're going to say that's vw evaluated at the limits minus the integral of w dv, right? So let's now plug those values in. V was e to the minus st, w was f of t, and we evaluate that at t equals 0 minus and infinity. That's our vw at the limits. And then we have minus the integral from 0 minus to infinity of w dv, which is this minus s e to the minus st dt. The first piece, we have e to the minus s infinity f of infinity. That's the upper limit, minus e to the minus s 0 minus f of 0 minus. And we're assuming that what we are Laplace transforming is well behaved, this waveform f of t. So f of infinity is a bounded value. That's what we're assuming for f being well behaved. So that now when it gets scaled by e to the minus s infinity, it gets annihilated, doesn't it? So that this guy is 0. What's this piece? E to the minus s times 0. That's e to the 0, which is 1. And I still need to do my integral, don't I? But if I pull that down and look at what I have a minus s. My integration is with respect to time. S can be factored out. And I'll leave everything else inside that integral, but now I have that's plus, whoops, s times this integral from 0 minus to infinity, f of t, e to the minus st dt. If I pull all of those pieces together, I end up with minus f of 0 minus. So I have 0 minus 1 times f of 0 minus plus s. And what's that square bracketed expression equal to? That's just f of s, capital F of s. And that's then the answer to our y question. We've now shown that the Laplace transform of a derivative is s times the Laplace transform of the waveform without it being differentiated minus f of 0 minus. And that's that argument is time t equals 0 minus. Questions on that? Let's then apply that. We now know how to Laplace transform at least a derivative. Let's look at an example where we are taking the Laplace transform of a differential equation. Let's step this up a notch. So suppose that I now have the second derivative of x, that's what the primes mean, plus 3 times x prime. So the second derivative plus 3 times the first derivative plus 2 times x is equal to v of t. And x might be the voltage across a capacitor, for example, in a circuit. And v might be a voltage source. And you're exciting this circuit with some v of t, little v of t. If you want to go home and discuss this with your roommate, then you might want to tell your roommate what kind of an equation this is. And this show is rated G, so you need to use the right terminology, right? Can't be swearing at this second order differential equation. This equation is a linear, which is good. That means we can use Laplace transform techniques. It's time invariant, which means your coefficients are constant. That means your R's, your L's, and your C's aren't varying with time. Those are fixed parameters. So if you're given now this circuit that has a combination of R's, L's, and C's, those R's, L's, and C's are fixed values. You've gone up to Josie in the stockroom and you say, I need a 10 millihenry inductor, I need a couple of, or three 2 microfarad capacitors, and I need some resistors. Give me a 1 ohm and a 20K ohm and a 5 ohm resistor. Those are all fixed, we're assuming. They're time invariant. You put your circuit together today and measure it. You put the same circuit together in a week and measure it, you should get the same results. It's invariant with respect to time. And we abbreviate that to just say, oh, this is an LTI, a linear time invariant equation. And if we really wanted to get colorful with our adjective, we could say this is a second linear time invariant second order differential equation, because you have two derivatives. Or you have a second order derivative. Now, what we want to do is Laplace transform that. So we're now Laplace transforming the left-hand side and that better equal the Laplace transform of the right-hand side. And because it's linear and time invariant, we can pull all of these pieces apart. We can just Laplace transform the second derivative of x. We can Laplace transform 3 times the first derivative of x separately. Or we can pull that or push that Laplace transform through. It's a linear operation. Meaning we can now say that that's the same as the Laplace transform, of x double prime. Plus, and that 3 can be factored out. That was our capital A from before, homogeneity property, times the Laplace transform of x prime, plus 2 times the Laplace transform of x of t. And if we don't know what v of t is, we just say, oh, generically it's capital V of s, which is defined to be the Laplace transform of little v of t, that waveform. Now, I threw a little bit of a curve on us because we didn't derive the Laplace transform of a second derivative, did we? But we just kind of chain that process together, don't we? What if I just apply one, or maybe I view x double prime as like a g prime, and now I know how to Laplace transform of g prime. I would just take s times the Laplace transform of g prime, of g, which was actually x prime, and then what do? I subtract off the initial condition, don't I? Which is x prime of 0 minus. Question? So now all I've done so far is the green right now is only part of the way finished with Laplace transforming x double prime. I'm not yet finished. And all I've done is I'm trying to do it in stages consistent with what we've derived. We've derived the Laplace transform of a derivative. That's all I've done. And so now you could think of viewing x double prime as like g prime. And so now I have s Laplace transform of g, but g was just x prime, minus g of 0 minus, but again, g was just x prime. Now I need to Laplace transform x prime, and that we've already done. That's s times x of s minus x of 0 minus, plus 2 times Laplace transform of x of t, which is just capital X of s. And that's equal to v of s. Now I simply need to finish that one up. But I know how to Laplace transform a derivative. But I need to keep track of that s out in front. So now I have s times the Laplace transform of a derivative, which is now s x of s minus x of 0 minus x prime of 0 minus, and now I just copy down what I had before. Let me push that 3 through. I could say I have 3s x of s minus 3x of 0 minus plus 2 x of s is equal to v of s. Where are we at? So the second line, this one, is that okay? So I haven't, the line above is where I'm doing the second derivative expression. So this, if I was a little bit taller, there's my s squared. And so when you now have a second derivative, you should be expecting an s squared popping out. When you have a first derivative, an s. A third derivative, an s cubed. A fifth derivative, now you have an s to the 5. So you're anticipating those terms correctly. If you keep track of all of your, if you have non-zero initial conditions, now all of those need to be accounted for. And if I now collect terms, meaning let me combine all of these pieces that involve capital X of s. And doing that, I have this s squared. That's this piece. I have a 3s. That's this piece. And I have a 2 right there. And then I need to make sure I'm keeping track of my initial conditions. And I could say, well, I have an x naught and an x naught there, but the first one is scaled by an s, so I have a minus s, and I have a minus 3. And finally, I have that derivative, the derivative of x's initial value at 0 minus, which is minus x prime of 0 minus. And all of that is equal to capital V of s. And what I want to do is I want to find little x of t. I wanted to solve this differential equation. I wanted to find what is x as a function of time, little x of t. What I want to do then is solve for capital X of s, and then I'll just do the inverse Laplace transform to figure out what little x of t is equal to. If I now solve this for capital X of s, I have a couple of pieces, don't I? I have a piece that involves all of those initial conditions, all divided by that characteristic polynomial is what we'll call it, but that's characteristic of the system that you've built. That's a property of the system. It's going to behave a certain way. It's going to give you certain dynamics based on the roots of s squared plus 3s plus 2. And you can probably factor that, can't you? S plus 1 times s plus 2. That'll give you that. So now you know where your roots are of that. But I'm getting ahead of myself. Here we need s plus 3 times x of 0 minus plus x prime of 0 minus all over s squared plus 3s plus 2 plus v of s divided by that same second order polynomial. And one of the nice reasons why we play with one-sided Laplace transforms is their inverses give us unique values. So we don't have to worry about this region of convergence stuff. The one-sided Laplace transform is unique. Meaning if somebody gives us a capital X of S, we can inverse Laplace transform that to find little x of t. Or given capital X of S, we can now do the inverse Laplace transform to find x of t. The notation that we will use is we just put a -1 as an exponent on this script L. This is now representing the inverse Laplace transform applied to capital X of S, and that's going to give us or produce little x of t. Now, if we go back to our example, this little x of t naturally was built up of two pieces, wasn't it? We had a piece here and another piece right there. We had two parts to this Laplace transform, capital X of S. And you maybe are already familiar with that, but let's now write that explicitly into two parts. We now have this inverse Laplace transform of the part involving the initial conditions and a piece that was involving the original excitation waveform, this little v of t, maybe our voltage source. That was this 1 over s squared plus 3s plus 2 scaling v of s. Meaning this piece right here is going to provide for little x of t. This is the response due solely to the initial conditions. If we had 0 initial conditions, that term wouldn't be there, would it? So this is the response or the part of our solution, little x of t, that's due strictly to the initial conditions. Meaning, maybe somebody charged up the capacitors to some non-zero value before you turned on your voltage source. And now you're going to see transients resulting from those initial conditions. And maybe the voltage source that you applied is a sinusoid. Or maybe it's a exponentially decaying sinusoid. Maybe it's a step. Maybe it's a ramp. It could be a lot of things. But the second piece is the response due to the excitation source, little v of t. So the green circle is now our response due to the excitation function, where this was v of t. Questions on that? Now we can find the initial condition response or the forced response due to or as applied to a circuit. Now what we want to do is understand how do we find these differential equations for a circuit, and that's our quiz. Here's a circuit. There's our voltage source, V of t, and I'm just going to leave that as a general V of t. Then that's going to be going through an inductor and a resistor, and all of those are in series with a capacitor. And now maybe what I want to ask in this quiz find the governing differential equation. And can you do that? Can you do that on the test Thursday? That won't be on the exam Thursday, but it will be on your second exam. Okay? Or something like this. But if we're thinking about this, what could we expect? Or what thought process? Now somebody, what's this week called at Career Services? Or who's on campus? Career Fair, thank you. Everybody's dressed up, looking very sharp, except me. But anyway, where was I going? Career Fair. Actually, I have to go to that this afternoon. I'm looking for a job. After this lecture, huh? How do we think about this? What do we see when you see this differential equation? Oh, that's where I was going with it. I was saying, okay, career fair, you're going to be interviewed. Now you're in an interview and your interviewer says, here's a circuit. Can you tell me about it? Can you write the governing differential equation for this circuit? Yes, sir. So, good. So did everybody catch that? You have two, here's how I like to think about it. You have two energy storage devices in this circuit, don't you? You have a capacitor and its electric field, and you have an inductor with its magnetic field. And those two things can play together, but they're both storing energy, aren't they? Or capable of storing energy. So you have two energy storage devices, which means you probably should expect a second-order differential equation, or two coupled first-order differential equations. And where do those guys come from? Eli the Iceman, right? Like I said, I have to go talk to some employers later. Thoughts? What did we just say? We said that we have in this circuit two energy storage devices. This is what I'm wanting you to do. So on the exam, you see this circuit and you go, forgot. Well, you can at least start looking, how many inductors and how many capacitors do I have? And you can start hoping for partial credit, right? You can say, how many energy storage devices do I have? What's the order of this circuit? What should I expect? In this case, we have two energy storage devices, which says that our governing differential equation, generically, is going to be second order. we're going to have a second order differential equation. And what does that look like generically? We just had one, didn't we? But if you said, well, let's make it even more generic, I have some coefficient times, let's say, the second derivative of our capacitor voltage plus some coefficient, and these are constant coefficients because our R, L, and C are fixed, aren't they? We got those from the stock room. Those are constant. So the alphas will be fixed. This is now V sub C prime plus alpha sub 3 V sub C of t equaling beta times V of t. Now, how do we go about getting something like that from that circuit? Or now you could say, okay, it's a second order. This is what it's going to look like generically. I can't seem to derive everything, so I'm going to put some alphas in play and a beta in play and just go from there. That might be a good idea. If you can't get started on the differential equations, at least you can demonstrate, here's what you should see generically, a second order differential equation. And how do I solve a second order differential equation? I'm going to show you for a particular set of alphas and betas. But if we go back here, what are we looking at now? Can we get a little bit closer with understanding are these alphas and betas, what they look like? We have Eli and we have ice, don't we? Meaning, one of the comments earlier was, well, the current through that inductor is flowing through every one of those circuit elements, isn't it? I sub L of t. And we know Eli tells us the current voltage relationship of that inductor. And we know ice tells us how I sub L and V sub C are related relative to that capacitor. Meaning, if we simply looked at this and said, okay, here is what I will label as V sub L, here is V sub R, now I can write an equation in terms of all my V's just by applying KVL. I can say with KVL, I now have minus V plus V sub L of t plus V sub R of t plus V sub C of t, and I'm back where I started. That's equal to 0. Eli tells us V sub L of t, that voltage dropped across the inductor, is L di sub L of t dt. And ice tells us that I sub C of t, which in this case, since those elements were in series, that's the same as I sub L of t, is equal to C dV sub C of t dt. So that now what I can do is I can pretty easily now come up with two first-order differential equations that are coupled. Meaning, let me use this right there, and I now will have an equation involving I sub L and V sub C, and then I can have another equation that relate I sub L and V sub C, and there's my second first-order differential equation. Meaning, my first equation comes directly from KVL. That was now minus V of t plus V sub L of t, which is now L di sub L dt. plus r I sub L of t, that was v sub r, plus v sub c of t is equal to 0. Meaning my differential equations, typically what I want to do is focus on writing equations for the inductor current and the capacitor voltage. Those will be what we can call state variables. And this is now a first order differential equation with two variables, I sub L, the inductor current, and V sub C, the capacitor voltage. To find the second equation, I can just rewrite this second equation. I know that C, dV sub C dt, that's the capacitor current, but that's the same as I sub L of t. And if I wanted to, I could now use this everywhere I have an I sub L, couldn't I? I can now say, oh, I have minus V of t plus L times the derivative of that piece. So now I have the derivative of C dV sub C of t dt plus R times C dV sub C dt plus V sub C of t is equal to 0. And what do I have? Now I have my second order differential equation, don't I? I now have minus V of t plus LC V sub C double prime of t plus RC V sub C prime of t plus V sub C of t is equal to 0. Or if I wanted to make that look maybe a little bit more like the standard second order differential equation, I could normalize or make it a monic equation by normalizing the coefficient of the highest derivative to 1. I can divide everything by LC. Let me put the V on the other side, and I now have V sub C double prime plus R over L V sub C prime plus 1 over LC V sub C of t equaling 1 over LC V of t. And now I have my alphas and betas, don't I? I now have the alpha 1, I think that was scaling V sub C double prime. I've come up to that to just be 1. Alpha 2 is R over L. Alpha 3 is 1 over LC. Beta is 1 over LC. Now if I can solve that second order differential equation, I've found the capacitor's voltage. Is that clear? So I will see you maybe later this afternoon or this evening about 6. But make sure I see you on Thursday. Our exam is Thursday. Homework number 2 is due by 4 o'clock today. Good luck with the career fair.